So today I decided to show you two different stories. One goes with the movies and some comments, etc. And then I felt obliged almost to leave a talk on not polynomials and applications as an appendix, so that you are free to think that maybe is not so much related to fluid mechanics, or maybe it has potentials. Okay, so this is the philosophy. Well, I start with very well-known movies. This is a simple simulation. As you see here, is meant to be a leapfrogging of vortex rings. In actual fact, is not really a leapfrogging, is a merging that takes place. It's a very short movie, and so I just like to show you, to show you, let me see how to go back. Maybe like this. And you see here the merging. And the merging, remember, the merging is because the vortex cores are of the same vorticity. Okay. And I'm sure you remember this morning when I showed you the two cross sections having the same sign. Now here, this is an old movie by Lehman Nichols. I'm afraid, everything is within 1 second. So I show you the movie and then I try to show it again. This is leapfrogging in water. And so you see really the mechanism that has been presented in action. Okay. Oops, let me try it again. I have to learn how to use this. Okay, so let me try it once more. Okay, here you are in the situation where the smaller ring goes through the other. Of course, it's in water, and the vorticity is as localized as possible. This is the nozzle, etc. Very hard work. And the two made this experiment in water. This is very, very beautiful, and it was referred to by Professor Pumir. So this is an old movie, 92. It got a lot of attention because it was a Nature paper. Head-on collision of colored vortex rings. I'm sorry, but the resolution of the image is not so high, but anyway, is very beautiful, and I like to play it a few times. So here we go. That's the Reynolds number, and that's the mechanism. As I told you, I'd like to play it again, and so okay, you see immediately here the little wake. People start to think to reproduce this in the labs in many parts of the world, and then they soon realized that it's extremely difficult. You need engineers rather than students, graduate students, although they are clever, maybe graduate students more than engineers sometimes. Anyway, the vortex rings are fat. They are not thin rings. And of course, you have to be extremely careful to shoot them coaxially. And the other difficulty is that they wanted to have, one in red, one in blue, all the time. Just to give you an idea, all the time that you do an experiment like this, you have to clean up completely the system. And so it's really a pain. And then, it's extremely important to have the two rings shot exactly on the same axis of symmetry. You want to have linear momentum exactly zero. Why? Because you want to see with the linear momentum zero where the momentum goes. And the momentum has to go radially away, like radiating away from the plane of collision. Here we are very, very close. They get slightly fatter and fatter, and they squeezed one against the other. And then, look, this is a kind of beautiful vortex surface, and you see here the various stages of the reconnection. So the vorticity reorganized, forming all these kind of elliptical vortex rings, and then these vortex rings separate and open up in this symmetry plane. And if you inspect this movie closely, as keen as possible, you will see that each ring inherit part of the blue and part of the red from the original rings. By the way, you see these instabilities in the vortex surface. I'd like to run it once again. Oops, sorry. I'm sorry about this. Okay, and you have it. It would be very nice to have a way to model mathematically the transfer of the linear momentum into this surface. This is a wavy surface, and the waves are inherited from the reconnection of each little ring, and it's just beautiful. We saw from Professor Poumir, I think yesterday or 2 days ago, that of course you can go to finer details with modern technology, and you really see the transition to smaller scales, etc., etc. Right. Now this is the movie that I'm very happy to show you. Alexienko et al. In Siberia is an old department that they have remote in the country, and I was invited by them when they produced this, and this is now a paper. I'm sorry I forgot to put the references, but if you type the name and the year, you find the paper is an English translation of a Russian paper. They produced collision and interaction of vortex tubes in water. So what you don't see, the black part, is entirely filled by water, and they had the work to focus camera on the spot where the reconnection takes place. Evidently, you have to imagine there is a camera. This is, by the way, this is a conic, cylindrical conic region. And the camera is focused after so many trials of where the event occur. It's conical for a number of reasons, including the fact that it enforces to have the key event localized in space as much as possible. Okay, here we go. You have, in a slow motion, you have a vortex tube here. And then you look at these two strands, they are almost orthogonal, and then they become anti-parallel, and they merge and they separate. I show you it again. So you see, by the way, another structure there, and this is the work that took them busy for a number of years, I should say. You see, is one tube, and then the two strands approach almost orthogonally, but when they are very close, they go anti-parallel. I show you again. Okay, you see they are getting closer and closer. Now here, one strand, these strands start to become almost in an anti-parallel fashion. You see, of course, the little bubbles there, and as we progress in time, you see really the kind of fusion process that goes on. And then here you see what in fluid mechanics people call it a bridging or a threading of vorticity, as a weak vorticity that survives through the process. And this is captured apparently well by modern direct numerical simulations by a number of people. And so this is the process. Of course, this is a separation of a separated, say, vortex ring, and there is a high twist in this region. The business is, as they know, to now identify the transition or the transfer of a twist in this event. Okay. Now this you know, because it's the first video I think that Professor Vega showed you, and is the formation of a trefoil knot, and of course it received a lot of publicity. You remember this is an airfoil made into the shape of a trefoil, and you know, when you take your flight from one place to another, you look at the wing, and very often at the tip of the wing, a vortex, low pressure field is produced, and the vorticity is visualized by vapor or whatever. And so the movie just, I just run it again. The airfoil is retracted impulsively, and you have this beautiful realization of what we may call a trefoil vortex knot. Then something important appears here. I'll tell you in a moment. And then again, as something else happens there, and then you cannot no longer follow the structure. Let me play it again, and I'll stop in at critical. Okay. At critical times, so we have the evolution here. Still, you can detect well the distribution of the bubbles in the shape of a trefoil knot. And then, as you evolve here, you see there is a reconnection. There is a reconnection, of course, has been analyzed in great detail, but the reconnection makes a change in topology. And what happens is that from one filament in the shape of a trefoil knot, you produce two highly convoluted loops, but they go one inside the other to form a Hopf link. So remember, one reconnection brings you from a knot to a link to a knot, etc., etc. One reconnection at a time. Okay, so system keeps going. You see the two looped rings, one inside the other, and then a further reconnection occur here. You see well, not in this frame, you see here just barely the two loops that are highly convoluted and completely separated. Another reconnection, you go from a link to the only choice you have is a separated unlinked unknot loops. So this is the idea. You take a trefoil, you allow to have a reconnection, and then you have a Hopf link of two loops, and then one highly convoluted loop. And if you can follow, you can trace the evolution of these bubbles still further, you may see the production of two separated smaller scale loops. So in, say, topological sense, drawing like this gives you the idea of the steps. Two colors, a link, one color, a knot. Now, this process was discussed experimentally 2013, and in the same year, I was actually a little bit earlier, I was informed about this remarkable experiment done at the DNA level. At the DNA level, you may provoke reconnection by using enzymes. Enzymes attack a polymer, and then they are called topoisomerases from topology, and there are several types. When I was young, they just were able to engineer one or two enzymes, say topo A maybe introduces a twist. Remember, it takes the polymer, it goes on a site, it opens up, so to speak, the polymer, it keeps the ends together, it inserts a number of twists, and then it reconnects again without changing, of course, the basis, the sequence, anything, just torsional energy. Why it does that? It does that because nature has found a way to compactify a very long molecule. And so by inserting twist, remember, is reminiscent of torsional energy. Torsional energy, if you think of torsion, highest gradients of length, gradient of curvature, and so it relaxes torsion into writhe. So twist is converted to writhe, and so instead of having a lot of twisting in the molecule gets rid of the twist and forms coils. And by forming coil, remember, you go down in scale. And so that's the key mechanism to compactify information. So evidently nature is very bright and clever, and in university now they learned to do that. In the old times you were putting books all around to display your books and your knowledge, and now to select a book you go on a particular room, and the books are all shelves in kind of files, and then you remove the files, so they compactify knowledge. And then if you want to have access, you have to access a particular shelf. Well, this is remarkable because you see the action of this enzyme provokes a sequence of transitions, and you see here the trefoil, and then the hop link, and then the unknot, and then eventually other structures. And they could analyze structures with higher complexity in topology, starting from this knot. Now, from a topological viewpoint, remember, from a topological viewpoint, we don't care about the geometry. So we can think of a diagram like this, and going from, say, the knot 2,7 to the link 2,6, etc., etc. And mathematically, that's the boring little part after the videos, and in the second part of today, I will tell you a little bit about knot theory and about how to analyze these things. Well, these things are particularly easy to analyze because, as you see, they can be thought as embedded on a mathematical torus. Indeed, this can be called a torus link. Remember, P and Q co-prime gives you a torus knot, and P and Q primes give you links. Okay, so this is just the idea. Right, let's see what I have next. Okay, so with Simone Zucker, and actually not only us, other people, Brachet in Paris, for instance, Giorgio Krustolovic in Nice, people around the world went for the Gross-Pitayevsky equation, because the Gross-Pitayevsky equation, the simulation based on Gross-Pitayevsky are completely governed by the equation itself. So you don't have to use Biot-Savart, you don't have to desingularize Biot-Savart. So it's quite a nice tool. And remember what I told you before, that it was demonstrated by Nazarienko and Bustamante in 2005. I believe that you can extract Biot-Savart from the Gross-Pitayevsky equation of a defect, of a vortex defect. Okay, vortex defects are empty tubes. So what you see here is basically an empty tube. You visualize your knot or your tube by deciding a threshold for density. So you think that the center line of this tube is a line, a nodal line, for the wave function where density is exactly 0. And then, as everything in nature is 0, and then climbs up to, say, some uniform density away from the condensate, but it does this climb in a region that is extremely small, angstroms. And so you can think that the tube is really empty, and then outside the tube, for simplicity, you think that density is almost constant. So it goes to 0 in an extremely short range of values, and you call this region a healing length or a healing region. All right, so we ran experiments. That's easy on a computer. So this is done by computational work, and we started at the time, this was done maybe 8 years ago, by a link. We are here, a link, a half link, then there is a transition, there is a reconnection at one place, and then further reconnection, and from the unloop this case we go to 2 loops, and we could because of the numerical work we could follow up this and this. There is a further reconnection here with the production of 2 rings, and these things you get a cascade towards the small loops as expected. Okay, so we wanted to explore this further, and the code of Simone Zucker is really a wonderful code, very, very precise, and in many, many aspects. Of course, you have a mesh that has to be rescaled at the points where you want to investigate the phenomenon further, and we could, recently, we could go to investigate the cascade of rather complicated structure. This is to some extent still easy. This is, as you see from the projected diagram, this is a knot, torus knot 2-9. Now, here I want to start telling you something. Now, we talked about, or at least I intuitively mentioned the idea of a cascade, of a topological cascade, but we identify 3 regimes that are to some extent well known in nature. One regime is classical, is the one you saw, the one that goes from complex knots to simple knots. One reconnection at a time, just because we wanted to understand the phenomenology. But of course, on a computer, you put this configuration in a computer, this is highly symmetric, and so you expect that maybe reconnections take place simultaneously, not one at a time, but many at a time. That's why we may expect a topological collapse. You go from, say, the idea is, okay, we may go from something like this, jumping down to this, and avoiding all these steps, all the intermediate stages. Why? Because the system is highly symmetric. That's why. And so, evidently, if it takes place not in one place, reconnection, but in many places simultaneously, then you jump straight to the unknot. Okay, so here I want to show you the simulation. Okay, simulation starts like this. I told you with like LIA solutions, you have a rotation and a translation. This is done entirely by Gross-Pitajewski. Now you see how it gets highly distorted. You have to expect that strands that get very close reconnect. So the transition goes from one knot to 2 loops. But these 2 loops, one is still highly convoluted. You see regions of high curvature. And so they get closer and closer. And in a moment, you see immediate, farther cascade towards the smaller structures. I run it quickly again, and so you can appreciate maybe the mechanism that I've been discussing. And of course, there are beautiful aspects here, symmetry of knot types, how the symmetry plays the role in this translation and rotation that you can understand even from the papers of Kida on LIA. And then this deformation, etc., etc. One loop, one other loop, two colors, but now they are totally unlinked, and then the further cascade to smaller structures instantly, because here we have 9 reconnections that take place because of the symmetry of the system. Okay, good fun for young people. Right, then the disappearance of these little loops are just due to resolution, or the fact that these loops are shot away from the center of the numerical box, say. Here, well, you read it, head-on collision. So we wanted to reproduce a limb work, and you saw it in water, and no wonders you can get the same under Gross-Pitayevsky. Again, this head-on collision gives you an instant cascade, a collapse of topology, because you expect that a number of reconnections take place at the same time. I think this is a very slow movie. Yeah, it's moving, but not so much. We have to be a little bit patient here. And you see it's deformed, and at a certain point, the two strands get closer because of the binormal flow due to curvature, and as they get closer and closer, at a certain point the reconnection becomes visible, and the rings, in this case I think we have 11 rings, and then of course you have these rings shot radially away. I'm sorry, it's a bit slow, and I can speed up the movie, but I don't want to make a mess with this. So you see it here. And this is just reminiscent of the reconnection of these vortices in the air that we saw through Crow instability. Maybe tomorrow morning we have the result. It's good for me. I can relax a little bit, and not too much though. Time to make phone call to girlfriends and boyfriends. Okay, we're getting there. I didn't pay attention to time. I'm sorry. I should have done that so that I would have trimmed down the movie. So okay, here we are, and as long as the iso density surfaces can detect the tube, we still see a tube, and then you see the formation of the various rings that separate away. Okay. Now this is for us the most interesting thing, because I wrote a little paper many years ago on the fact that, well, Kelvin wanted to produce a vortex knot. So William Irvine did produce a trefoil knot, and of course it got a lot of publicity, perfectly okay. Problem is that is not exactly what Kelvin wanted to do. Sorry for big journals like Science and Nature and blah blah. Because one thing is to show a trefoil knot, and the other thing is to do exactly what Kelvin wanted to do. Kelvin wanted to shoot two rings, say trivial topology, so to speak, and then create a knotted structure from the reconnection of two unknotted loops. So we wanted to do this because you remember we had a cascade, and that's the natural phenomenon. But what about going backwards, i.e. forcing things to go backwards? however, leaving the natural Gross-Pitayevsky acting on this. What I want to say is that in nature, you probably can produce a trifoil knotted filament, even in water. But you pay a price. The initial conditions have to be extremely precise. In other words, for example, no symmetry. No, not at all. Otherwise, if you have two loops that interact, you may have 4 points of reconnections. You want to break this symmetry, and you want to produce one reconnection at a time. And that's why it's so difficult to produce a trifoil knot. You have to know the right initial condition for the equation to integrate and get the knot. And this is very, very hard. But with numerical simulations, we can do that. We can prescribe in initial geometry, guessing what would be the exact location for one reconnection at a time. And if we do that, and we are a little bit lucky, we can go backward in the cascade. Remember what I'm saying. I'm saying that is not unnatural. It's very, very improbable. That's why it's hard to see it. And so here there is no initial, let's say, trivial topology. Two unlinked tubes. And I want to see if it's possible to create a knot. So I'm starting from, I'm starting from this part of the cascade, and I'm going backwards. Two colors, two loops that are unlinked. Then somewhere a reconnection will take place. Okay, one color. It means we have the production of one filament, Hopf link in a moment. Okay, here is a Hopf link. One inside the other, and then a further reconnection. And there we have it. Wait a sec here. Okay, this is a trifoil knot formed. So this example gives you a lot of information, not technically speaking on the numerics, etc., but conceptual ways to understand why it's so difficult to produce a trifoil knot. I wrote a kind of conjecture, a thought, a long time ago, saying, well, if you take two elliptical rings and you work out with the mathematics the curvature, and you shoot one against the other appropriately in time and space, then they will reconnect at one single place, and then they form a Hopf and then the trifoil knot. So this is hard to prove, but with numerics we can explore these things. All right, so because of Didier mentioned minimal areas bounded by vortex lines and vortex filaments, I included this picture. I'm sorry, it's hard to understand it, but imagine, you see here the 2-9. So we start with all the knots you saw, even others. We started with all torus knots up to 2-9. We let them evolve. We did a lot of, Simone did a lot of work on analyzing things. And at a certain point, we had the idea to look for the Seifert surface bounded by the knot. Remember, it's an orientable surface. And we went for the minimal area, like soap films. And what you get is that the minimal area always decreases, and these points, for instance, in this case, denote reconnections. So you can prove this happening for all the knots and links we tested, and then we went for the maximal of kinetic energy and sort of energies that you have involved. This particular energy is so-called quantum contribution. You see, it involves gradients of the density rather than gradients of velocity. So basically, these are the two aspects. And what you get is you consider this D is Dirichlet energy, and you approximate the exact Dirichlet energy with this one. And the approximation is extremely satisfactory. You have to neglect a region where density goes exactly to 0, which is a region of very high gradients. But so we take into account the gradients, but not the surface. Okay, the surface is really minute compared to the other values. And this is done for all knots and links. So this is just to use minimal surfaces to detect defect dynamics. All right, so I'm just on the closing here. The point is, I told you before that people were kind of joking with me many years ago. Knots and links, I mean, is some fun for you, Renzo, but they are not in nature. And I said, well, okay, maybe not in real fluid mechanics, but in superfluid, which is real, superfluid helium or other context, they can be found. And this is a work done by the group of Carlo Barenghi in Newcastle. It is an amazing piece of work because they could extract from a tangle of filaments of vortex lines in the superfluid box produced numerically, but one of the codes that is well known in the world. And then they extracted elements that are contributing to this tangle. They analyzed one filament by one, and they could show the production or the presence. Of course, is something that evolves in time, so expect reconnections, etc., etc. Some of these elements are knots of an incredible complexity. So when he got this information not long ago, the paper is, you see the date is 19, I contacted immediately many of these great knot theorists around, and nobody, I mean the knot tables available for highly complex knots are not able to determine the polynomial of these knots. So they were used simple polynomials, for example, Alexander polynomial. One quick information, of course it's not precise, but just to have an idea, these polynomials, I'll introduce these polynomials after the slides, say the power, the highest power of this polynomial, more or less gives you the idea of the complexity of the knot. So they got polynomials to the degree 30, and that means we are millions and millions of knot type before getting to that power. So it's possible to analyze the topology to some extent. And of course, the business is, as usual, in turbulence, relating not only topology with the beauty of what you get, but the energy transfer and all that. So this is the business that I'm keen to focus on. Now, you saw the cascade before, torus knots and links, and I'll introduce as an appendix a little bit of knot theory to show you what we did. But before doing that, I want to conclude with the slides. So let me jump to the conclusion of the work of knot polynomials in fluid mechanics. So we developed adapted polynomials from knot theory, and by using standard knot theory and polynomials and combining this information with helicity, we could prove mathematically that the system has a decreasing monotonic decrease of energy in terms of complexity. So you can reproduce the pattern that you saw before. We were, for example, here the trifoil knot, the Hopf-link, the unknot, and the smaller rings, starting from we just showed the 2, 10, and then down the others. And these are just the numbers, total length, kinetic energy, bending energy, rife, etc., etc. It depends on the scale you put them. Anyway, all these numbers goes down. And this was done by using not polynomials, let's say adapted knot polynomials. So they are not exactly the knot polynomials of knot theory. They've been modified, and I will tell you something about that. Now, this is not the whole story. This is 2016. So we started saying, on the basis of the information that was around, well, a knot like this can reconnect somewhere here or somewhere there, or maybe two places, and go in another direction. Why to follow all these paths? This path would be the most general, natural path, the most probable path, but maybe certainly not unique. And so this is a modern work that was done with Xin-Fei Li and Xin Liu. And it's a lot of work behind this. Xin-Fei did a lot of calculations, starting from our adapted polynomials, the way I'll present them in a moment. You consider possible different paths. And now the exercise here was to use this diagram with numbers, I think, in black, denoting the probability of the transition. And this diagram came from DNA paper, from a PNAS paper in DNA by the group of Mariel Vasquez and Arzuaga in Davis. And we wanted to use our technique to see if we were able to match this diagram. Now, the red numbers are the probabilities computed on the basis of the polynomials we introduced. And you see this is basically the path that you saw in the straight line, in the horizontal line before, the Q6, Q5, Q4, Q3, etc., and the probability is the highest. But of course, you can go to composite knots or to other types of links. Now, naturally, you can go even up. There are no arrows to go up, but why not? I showed you that we started with two unknotted, unlinked loops, and we went in this direction, up to the trefoil. So, you have to consider probability, and you have to consider some heuristics on the statistical distribution of these things, and then hopefully saying something that is useful for fluid mechanics. So I think it would be a nice idea to stop the slides and perhaps to do a little bit of work on my appendix to show you how knot polynomials are used in this. I'll be brief, don't be patient. So let's take a few minutes just to remove the screen and put the lights on. Okay, so thank you for being here in this last part. And I told you this is kind of appendix, topological cascade and knot polynomials. As usual, I'd like to give you an idea. We are all students, right? So we want to learn. I want to give you an idea of how knot theory developed. Don't worry, just a minute or two. Extremely short view of things. So, remember we started with Kelvin's program on vortex atoms, and Kelvin asked the younger Tate to tabulate knots. And so Tate worked on that and produced tables of knots. And these tables, he classified knots in terms of topology correctly by playing with by using chords on the floor and trying to find out differences in knot types as much as he could. I told you about the blues of the knot theorist, ups and downs. At a certain point, he realized that all knots were alternating. It was ups and downs in the crossing, apparent crossings, and then overpasses, underpasses. And then he realized that no, that wasn't the case, so he got depressed. Meanwhile, he received a letter from Maxwell saying, well, we have linking number, but in some occasions, the linking number fail, and you know why. We discussed that. Whited link should be called Maxwell link, and the Borromean rings also. Another point of depression. And then at a certain point, he said, what about knots? And he got very close to the idea of the self-linking number, very close. Maxwell to Tate said, well, if you think of a kind of ribbon and the edges of the ribbon are like a link, then you are getting to the linking number of Gauss. Can you do anything about that? And nothing came out. Anyway, he published the first table of knots, and then he kept going and going. And so he classified knots up to 10 crossings with basically many knots. I can't remember how many, hundreds, and no mistakes. In 1974, Perko from Japan showed that the two knots are actually the same knot type. So there was a duplication, not really a mistake, but okay. Then nothing happened for several years, and in Germany, Reidemaster, we are already 1920s, Reidemaster introduced the moves that I mentioned very quickly on the board, just to show that from a diagram of a knot, you can go to another diagram, another geometry of the knot, without changing topology, if you were using his moves. These moves led Alexander to implement some ideas in the United States, and he implemented the ideas, and let's say, allow me to say that he got the polynomial of knot, the first polynomial of knot that bears his name, Alexander polynomial. Polynomial that wasn't so effective, but anyway, it helps for simpler knots, and then it fails in many occasions. Things went quiet again, and then at a certain point came Conway, 1970. So we have to jump almost 30 years, and Conway made an amazing contribution. He revisiting Alexander's work, he discovered Tate that was totally forgotten. And by discovering Tate, it applied and studied this knot invariant. I'll tell you what I mean by that, based on Alexander, and introduce other type of invariants, let's say Conway invariants, let's call them that way. Meanwhile, there was a new way to see things apart from pure mathematics. Of course, I'm just pictorially giving you some information. And the new way was to think of a knot in the shape of a braid. So you construct the knot as if it were drawn in a on a mathematical torus, allowing, of course, overpasses, underpasses. And then after Conway, things start to be busy, because at a certain point came Jones. Jones was working on some aspects of physics, or mathematics of physics, Young-Baxter equation. He realizes that the Young-Baxter equations are kind of reproducing, so to speak, some scheme that was encapsulated in Alexander. He refined the scheme, and he got his famous work on the polynomials, and the Fields Medal was awarded for that. And then, Witten went his side using Jones polynomials for high energy physics, and many people discovered alternative forms of these polynomials. So around Jones, we have the Kaufman brackets, and then a group of people, Humphrey PT, acronym for several people working together, they came up with a more sophisticated polynomial, so to speak. Then things went still on till Vasiliev. We are 2000, and Vasiliev unified the view of various polynomials, and things were started to go in the direction, let's say, of homology. Came Kovanov, and they resurrected the Floer homology, etc., etc. So things went in another direction, and this is the modern state of things. I'll show you something about polynomials, and my aim is, well, Emmanuel is a busy man, and he told me, well, I have 15 minutes for your knot theory, so do what you can, but I'm busy. Okay, so I'll try in 15 minutes to tell you what is a knot polynomial and how to use it, right? So allow me to be a little bit superficial. Remember that we start immediately with a definition, okay? So we cut the long story short, and I start with a polynomial that is not the simplest. Sometimes you know, it's good in maths to start from simple things, but you will see how it works. It's so easy. So let me say, okay, let's give a definition of this polynomial. A definition goes like this. Let U1, I identify the unknot by U1, and remember, we deal with oriented knots and links, so there is always an orientation on my diagrams, and these denote the unknot. The unknot. I'm implying a continuous deformation of this, so it can be highly twisted in space, but it's still the unknot, and oriented, and K, an oriented knot or a link. I won't make any difference between them. I introduced the Humphrey. Sometimes they say Humphrey PT, polynomial. The Humphrey PT polynomial P of the knot K is a polynomial of the knot in two variables, A and Z. Function of the dummy variables A and Z, and is defined by the following relation. Two relations, say P1. This is the first relation. The polynomial of the unknot is 1. Whew, okay, this is not so difficult, right? The polynomial of something else, more complex, is based on this Skene, what is called the Skene relation. A polynomial considered at a particular crossing site, bear with me that I'll explain what I mean, minus A minus 1, the polynomial of what I get by switching the crossing to the other type, and this is Z times the polynomial on when the crossing site is smoothened out. That's the language. Where of course, by this, by the other one, and by this, I denote, respectively, overcrossing, this case, overcrossing, undercrossing, or underpasses, undercrossing, and smoothing, of a distinguished crossing site. Okay. I can't remember the names of all these people. L stands for licorice, the man who taught me knot theory in Cambridge. M, millet, Okneanu, Yete, and these are good exercise to write because they are Polish people, good friends of mine, and impossible. So the pronunciation goes Przyciski, has no vowels, but Przyciski and Tracik, Paweł Tracik and Joseph Przyciski. Przyciski is now at Washington University, Tracik is still in Warsaw, and others. Okay, so this polynomial came later than Jones, okay, and it has, as I said, is a polynomial of two variables, and now I'm going to tell you. So first of all, what we are going to do is to construct Laurent polynomials in variables a and z. These variables a and z can be combined together, so the polynomial can be reduced. When we combine these two variables together to one, we get the Jones polynomial. Okay, so Jones polynomial is a particular case of Humphrey PT, but you can reduce Jones as well, and you get Alexander polynomial. So you go back in time, so to speak. Of course, in modern times, you may read about the polynomials of 3 variables, 4 variables. I mean, people try to understand if there is any structure, and of course there are structures behind, etc., etc. Now we want to understand immediately how these polynomials work, and so you understand what I mean. And in order to do that, I'll do an exercise, and I claim to offer you the shortest possible path to understand how this polynomial works. Remember, Emmanuel gave me 15 minutes. I used already maybe 10 minutes or 7 minutes. I have to rush. Okay. Sorry. I need these two relations, P1 and P2. Okay. So my worked out example is so easy, right? So let me start with the unknot. So this is example, a way to apply this skin relation. So the unknot, I can consider the unknot, U1. You know what is the polynomial of the unknot, right? The polynomial of the unknot, P, is written here. First relation is 1. Okay, and then I consider, for example, this case. I know what you think. So, arrows like this is a plus. Let me call this quantity, if this is U1, let me call it for the moment gamma plus. But I know what you think. Is the unknot. Is just that deformed, okay? Right, gosh, I have to do some work here. And the unknot has a positive crossing here. And the polynomial of this, hard work to be admitted to ENS, is 1, because it's the unknot. Okay. And then what I do, I deform this to the other one. And so the other one would be something like this, same orientation, except that now I have the different type of overpasses. Is actually an underpass. I call it gamma minus this one, which is the unknot. Okay, so I call it a P of gamma minus gamma 1, sorry, gamma plus is also 1. Phew, a lot of work. And now I consider the smoothing of the crossing. Okay, I have an apparent crossing here, the other apparent crossing here, and the smoothing. And the smoothing will be just this. Let me call this U2, just to say that these are two unlinked, unknot circles. And I want to find out the polynomial of U2. But the polynomial of U2 I don't know. So should come from this second relation. Right, let's work on this second relation. I have an A here, and then the polynomial of the positive crossing, this one, which is a 1, I won't put it, is a 1, and then minus A minus 1 times the polynomial of the other one. I take a crossing on the diagram, I switch it over, I have a new configuration, I evaluate the polynomial, this is also 1, I have equal to z times the unknown. This is the unknown. So this is the polynomial of U2. So from here I have that the polynomial of the unknown U2 is given by A minus 1 divided by Z. That's it. That's it. Of course, we can do this exercise on all possible knots and links. All possible knots and links. An example. Okay, another example. So, example. I take, well, I have here the, well, one of the many is the Hopf link. I take the negative Hopf link, just for example, one and the other like this, okay? And I pay attention to this particular crossing, okay? So that means that once I have a diagram, I focus on one single crossing, and one single crossing I work with this relation. So I distinguish crossing, I apply the second relation, and you see, there are many ways to read this equation, because I can start from this and say this is equal to the rest, or whatever. And so, you know, all the time I just swap the crossing and smooth the crossing, two operations, I get two different configuration, one of this type and one of this type. One type here is just, well, this is a positive crossing, and so I have to modify this into a negative crossing, right? So let's see if I don't make mistakes, but you please check like this, and then something like this. Let's see if what I copied is all right. So this and this becomes, the crossing here becomes a positive, positive, something wrong. Is it wrong? Yeah, why not? Positive, positive, negative, negative. Yes, is wrong. Please pay attention. Okay, let's do it again. Indeed, I know where I made a mistake. I think I made a mistake here, but we can go on like this. Why not? So I stick to this diagram. And this diagram, this is a positive Hopf link. I wanted to do the negative Hopf link for some reason, but I stick to this diagram, and then I have to convert this crossing to the other one. So I go like this, and the other one has to be low like this, right? Now, are we okay? Please check. Check yourself. Okay, I do like this. This is a negative crossing. This is a positive crossing. Now, what I get here is two unlinked circles. Now, I want to do the smoothing from this. So what I do, I go like this, this. So I have to do like, let's see, like this, like this. Let's see if it is correct. Okay, so the smoothing is like this, is on this crossing. So I have to follow the orientation. And on this trend, I'm okay. Then I go down, under. I go under, then the smoothing. Remember? The smoothing here. So it's okay. Like this. Right? So this is the unknot. This is the single unknot. So this is U1. So I can get the polynomial of this because this is 1, and this is the polynomial of the off-link. So if I know the polynomial of the off-link, okay. Otherwise, I have to use the other information. Let me use, again, a third example. And the third example is about the trefoil, example 3. And the trefoil, I want to take this trefoil for some reason. Oops, like this. Oops, like this. Right. So I have this, go on like this. So I have not too many arrows, but I need arrows. So I have a minus here and a minus there. I'm just checking if it is correct. And a minus there. So this is called the left or the negative trefoil. Okay. In generally, when I drew trefoils during the course, I used the positive trefoil. But it doesn't matter. I just... Okay, so this is the negative trefoil, and what I get when I do this, well, I consider, for example, this crossing, and I work on that. So this is, as I said, the negative crossing. I have to swap the overpasses, so like this, like so, and so. Let's see if it looks okay. So this crossing is there. This crossing is there. That's okay. Now this has to go over. It does. And then under. It does. So you see, this crossing becomes now a positive crossing. A positive crossing. If you pay attention, this is the unknot. This is the unknot, because there is a kind of coiled region here that you can remove it by a so-called Rider-Master 2 move, and then there is a twist over that you do with the Rider-Master 1 move. So this is the unknot U1. You know the polynomial of this. Now let's do the smoothing there. Okay, so I have something like this, and like this, and then something like this. Okay, let me see if I copied correctly my picture. I have to do a smoothing here, and then I go in that direction. All right. Then I come back. I go over. Yes, I go over like this. Then I go under. And so this is okay. Let me see on this side. I have to go this way. It goes over. That's okay. The smoothing here. So it comes back. And that's it. So here we have... what is called, this is a negative, and this is a negative. So this is a Hopf minus. Hopf minus. So you see, the Hopf minus can be obtained as well. I had in mind to show you the Hopf minus. Well, we can do it, but you understand what I mean. Oh, we can do it. We can start from the Hopf minus. And so I replace my Hopf link that I did before. I have to pay attention. There are very small diagrams on my notes, and so that's why I get confused. All right, like this. Arrows, one, the other, arrows here, etc. Now, this is minus, yes, and this is a minus, yes. So this is definitely the Hopf minus, and we'll see where we go. So we just exchange the crossings there, something like this from here, and then I go down like this, I go round like this, I close it up, so it seems that this is okay. And so I have the two unlinked loops. And from here I smooth the crossing. So I go like this, I go round, then I come back, and you see, it goes exactly as before. You know, this is the smoothing. I have this curly thing there. And, okay, so this is U2, and this is U1. From this case, it's clear what I had in mind, my little program, because my program was, okay, I derived the polynomial of U2. Now I know this is 1, and this has just been calculated, so I get the polynomial of H minus. When I have the polynomial of H minus, I come here, I consider the trefoil left, and then this is known because I just computed, and this is P of U1, which is 1. So I get the polynomial of the trefoil knot. So I took a little bit more, 15 minutes, but this is, I know he's not happy, but this is what I could do. You have polynomials, and you keep going with complexity. You go up in complexity. So one possible thing to do is to go to a knot atlas, one of the many, not so many, there are 3 or 4 very amazing websites. Knot Atlas is an effort of mathematicians to put on one website all possible information about knots. So you go there and you find so many information. I think it's a project by Barnatan that started years ago and it keeps going. So you find geometric as well as topological properties, certainly polynomials calculated down to quite high number of crossings. And remember, as you go up in crossing number, topological crossing number, for example, 6 crossing, you may have more than one knot type. And this number increases exponentially with a topological crossing number. So the 3 crossing is just a trefoil, the 4 crossing is just 1, 5 crossings you have 2 knots, the 6 crossing I think 3, and so on and so forth. So it keeps increasing, and I can't remember how many millions of knots have been classified so far, and up to a certain number of crossings you have the polynomials. So polynomials are there available for you. There are beautiful softwares, in particular one software almost free is Knotplot, and it costs $30, something like this, by Rob Sharine. He's an amazing tool, Rob Sharine. And you know, with Knotplot you can investigate many properties. You can make up your knot. You can invent, draw something on a paper, overcrossing, undercrossing, give it to Knotplot, and the Knotplot explores the knot type. It gives you all the basic polynomials you like. And then you can do more than that. You can put charges on your knot. You can put physical charges, mathematical charges, charges that do not obey nature at all. You can change the exponent of a Coulomb, say, force, and see how it goes. So some of these knots will relax, some will expand. For example, if you take a charge and you put positive charge everywhere on these strands, then the knot will start to move one from another, and so they get to some kind of minimum energy state, and by exploring minimum energy states you may find symmetries, particular symmetries. Or you can do the other way around. For example, you can think of a line being a magnetic line, and because you know there is a Lorentz force curvature along the principal normal, then they will shrink. And you imagine that these knots have a volume, and indeed you can do that with Knotplot. There are tubes. You can center tubes on these lines and prescribe the fact that, for example, the volume is preserved. So you are thinking of a volume preserving diffeomorphism of the given knot. So what happens is the knot will, because of the Lorentz force, will get to shrink. And as it shrinks, the volume will get fatter and fatter because the length will get shrunk. And as the length gets shrunk, the cross-section increases. And increasing the cross-section will reach a point where it can no longer relax. And you call that a tight knot. It's like inflating a balloon, but instead of a balloon, you inflate a tube, an elastic tube or something like that. And this is a beautiful problem. I think I investigated the problem as following the advice of Keith Moffat. He has a number of papers, one in Nature, by the way, of 92, more or less, where indeed you can explore the ground state energy of knot types. And I used the data sets that were provided by exploration on tight knots that are available on the Cantarella site. Cantarella was one, and co-authors to have worked on ridge runner software to knot tightening. And so you can explore many properties of this tight knot configuration. When you go to the minimum energy state, you get to some extent to the steady state of magnetohydrodynamics, of magnetic knots. And in that state, you can establish a correspondence with the steady Euler equation of vortex structures. Now, what's the bottom line? I have only a couple of minutes. I take these minutes to show you the connection of, say, knot theory to fluid knots. And the connection is a bit elaborate. That's why I cut it very short, because I cannot go into that. But is based on one fact. First of all, consider these tubular knots as fluid knots. And second, you think of these fluid knots as thin tubes where there is, of course, a vorticity in there. And your fluid knots will have a helicity associated. But the helicity for thin tubes, you know now, U dot omega in dV. But then if the cross-section is very small, you can think of representing this helicity as a circulation, averaging vorticity over the cross-section, and then you are left with UdL. And this would be on the knot line. So this is, you may think of this as a center line helicity or something else. You can prove that it has topological properties under some mapping, and that makes it interesting. Remember that ideally this is related to the same integral in the abelian case of Chern-Simons theory, A wedge dA. A is there the vector potential, and this is the vector potential for the vorticity. Now, if you take this, now I consider Humphrey PT. I said that, I didn't say this, but we can do it. We can do it quickly because we can show, I'm sorry, I just forgot, but we can do this. Let's see if I have it somewhere. If we take A equal 1 and Z equal, well, let's say tau half minus tau minus a half. Remember, for the moment, these are dummy variables, no meaning, no physical meaning. Okay, we will give it in a moment, but for the moment, these are dummy variables. Then you can reduce Humphrey PT, Humphrey PT to Alexander. and the Alexander polynomial is given, generally is denoted by delta of k, and this is the usual relation, is the delta of the unknot is equal to 1, and then you have the recursive relation yes, I have to correct what I've seen. Anyway, delta of what? The positive crossing, and then minus delta the negative crossing, and then this is tau half minus tau minus half of delta of the smoothing. And if you want to go from Humphrey PT to Jones, you do the following. Again, Jones is often denoted by V of k, and similarly you get the V of the unknot equal to 1, and if you do the Jones, where I put my new variables, A is equal t minus 1, and Z is equal t half minus t minus half. And so the polynomial goes like t minus 1 V of the positive crossing minus t polynomial of the negative crossing equal t to the half minus t to the minus half, and then you finally have the V of the smoothing. I'm sorry, I wanted to conclude with at least mentioning this. Now, what about helicity? Well, these you can prove rather easily that any of these variables, you assume, if you like, that these variables stay the same on the physical knot. Well, of course, it's a scalar. It's a scalar, and you say, okay, this scalar not only is transported by the flow, but is the same scalar along the fluid knot, whatever is the scalar. And so you can prove it's a little bit of work. The following theorem, this is due to Shin and myself, 2012. We used the first Jones polynomial. Let H be H of, say, our knot, fluid knot now, so it is of some finite thickness, be the helicity, or the centerline helicity. The helicity of the fluid knot, K. Then what you can prove is that e to h of k given by e to the integral, this quantity, integral of udl, appropriately rescaled. You can put gamma equal 1, or you can have your gamma there and then appropriately rescaled, satisfies with, okay, because in the construction you need some techniques, with a plausible statistical hypothesis. I can't go into details here. Statistical hypothesis, nothing terrible, but we have to be careful. The Skene relation satisfies the Skene relation of the Jones polynomial, V of k. In 2015, 3 years later, we showed that the same holds true for Humphrey PT polynomial. And now my time has run out, so I'd just like to tell you what are these variables. If you are in Humphrey PT case, I'm sorry. In the Humphrey PT case, you can relate A to twist and Z to writhe. And if you do this, you give immediately a meaning to these variables. In the case of Jones, you have only one variable, and because of this connection, you can show that A and Z are giving you a constraint on the sum of writhe and twist. In other words, helicity is fixed there. And these are called framed knots. And remember what I told you this morning, that helicity, for example, for quantum defects, is exactly 0, but is conserved. In other words, writhe and twist can commute, if you like. And this is wonderful because it's in line with some work in high-energy physics or the work we can think of for vortex defects. So because of this, you can do experiments. And if you do experiments, you can evaluate writhe and twist. Remember the torus knots? The torus knots were giving you a monotonic decreasing numbers, a function of these numbers, and these numbers were obtained by using Humphrey PT, by putting twist and writhe according to the average values of the system. That's why I put a statistical hypothesis, because you have to take average values. So it's not exactly A that is twist. It's a kind of something like this, okay? Because you have to average out the information. And then you can measure, you can quantify topology. You qualify topology through the polynomial, and you quantify topology through this approach. So the hope is to have a measure of complex systems that is new, goes over the problem, solves some of the problems of helicity when linking numbers are 0, because the polynomials capture this information. And the hope is possibly to establish a relationship between topological complexity and energy, a dream. Okay. Thank you very much for your attention. Thank you so much.